So today I am going to talk about some work that we've been doing here at the University of New Mexico using artificial neural networks with gravity and muon measurements for shallow subsurface density prediction. Now, you're all volcanologists, so probably don't have to go into too much detail about subsurface density and why it's important for volcanoes, but in short, we're interested in just figuring out what's going on underneath these monsters, especially for hazard monitoring. It has a lot of important implications. So just narrowing in on this picture, what we are interested in is subsurface density. And we're interested in using gravity measurements paired with muon tomography in order to do so. This is a pretty novel field. This was a pioneering study by this group in Japan, where they imaged the Shaoshin's lava dome. And here you can see a muon detector on one side of the dome and these gravity stations sort of dotting the top. And they've imaged the inside of this structure and paying particular attention to these high density anomalies at the top. We've done some work with muon and gravity measurements with a group at Los Alamos, just imaging this this high density structure beneath in the mesa beneath the town where Los Alamos here in New Mexico is located. It was deposited by the nearby Jemez volcano when it erupted about 1.2 million years ago. And we were looking to image this sort of sandwich structure. And we were able to do so using these measurements. A little bit about gravity. We are basically, a gravity measurement is just a tiny relative difference in gravity that we're measuring. And the relationship between a gravity measurement and a density is a linear relationship, and it's related with this GIJ kernel, which is just given by this integral here. Now, the problem with gravity, as a lot of people know, is this non-uniqueness problem. So this is illustrated here nicely, where we've got the same uplift or the same measurement at the surface could be due to any number one of these subsurface density anomalies. So this is why gravity needs independent constraints. And there are many ways in which people do that, but we are primarily interested in using muon tomography. Starting out to talk about this, we're going to talk a little bit about muons. They are produced in the upper atmosphere. They arrive at the surface of the Earth with a broad and continuous energy spectrum. And depending on the angle of incidence, the incoming energy, the flux, they can penetrate through matter quite a ways. And so for rock, this is a picture for standard rock, they can penetrate many hundreds of meters through rock. And what's nice about muons is the energy loss per unit length as they travel through matter is linearly proportional to density. So you can see here a similar relationship between, as we had with the gravity measurements, we have with what's called the range, which is we calculate from this dEdx value, which we measure. And so the range is linearly proportional to density through this Lij kernel. And this is just the path length through some ith element in our discretized domain due to some jth. We've discretized our trajectory, the angles of our muon trajectories too. So for some jth trajectory as it hits the muon detector. So we've got these linear relationships. That's nice. We can use those together. But also we have complementary sensitivities. So the gravity has this 1 over r squared, this very broad sensitivity. But again, there's the non-uniqueness problem. Whilst the muon measurements is a very narrow band. So we're basically limited to the acceptance range of our detector. So that's kind of another reason why these are nice complementary measurements to use. So the previous work that's been done with that group in Japan and the work that we've done has used Bayesian joint inversions to back out density structure from our measurements. But we are interested in this study in how we can use machine learning instead. So just to set up the problem for an inversion, you are trying to minimize some cost function given these known forward operators and some model estimate. And these known forward operators, again, are those calculations, the forward calculations that we just saw. For a machine learning problem, we're also trying to minimize a cost function, but what we're trying to minimize is the difference between a suite of input models and a suite of output models, and we're trying to find a set of weights and biases that maps our outputs to our inputs. And in this case, our outputs are some suite of models with different density values and perturbation geometries. And we create our inputs based on these forward operations and these suite of models. Within this, we can consider two different types of problem, which I'll go into, either a regression problem or a classification problem. So for the regression problem, we want to consider a continuous domain. So we have a finely discretized domain, and we want to consider continuous outputs. So those outputs, the inputs and the outputs are all continuous. And we have here a toy training model, which we've modeled after this lava dome from the Nishiyama study. And it's just a Gaussian hill with some muon detectors and gravity stations. And the measurements that each of these, the inputs that we calculate with those forward kernels are based on these random suite of outputs, which is just, we've placed some density perturbation, some spherical density perturbation in a continuous manner within this domain. We take its XYZ coordinates of the central point, and we give it some continuous density anomaly value. So here we can see that in our network architecture, where our input layer is just a stack of our gravity measurements with those range measurements. And we have some hidden layers, and then the output layer is a continuous value of that central, those XYZ coordinates, and that delta rho value. And as per usual, we need to normalize or scale the inputs and the outputs. So some results for this regression model. Here we have normalized values of the actual values and normalized predicted values. We did a grid search, and these were the optimal hyperparameters. And a one-to-one correspondence would lie along this line. So we can see here we've done pretty well, but we also have some ideas of what we can do to improve this. So that's the regression model. Now I'm going to talk about the classification problem, which is most interesting to us because it's sort of the most unique to using machine learning. So the regression problem is a lot like, probably the most analogous to inversion problem, but the classification problem is essentially a pattern recognition problem. And so the way in which we do that is we have the same domain set up the same way, except now we have very coarse discretization. So each of these is about 50 times, each of these elements is 50 times larger than the other one. And we apply to it various patterns of where there could be a density anomaly. And the idea is that we want to, so in this Nishiyama paper, you can see in this lava dome that they imaged that there are density anomalies that are different in space. So we don't want just a centralized location. So can we back out patterns of density anomalies? And the results that I'm going to show, since this is kind of our classification problem, is what we have is a bit preliminary. We've just kept the perturbation value, the density value fixed, but eventually we will want to modify it so that we can have differing values and be able to predict those. The network architecture is very much the same. The input's the same as before, but now the output is some stacked vector of zeros and ones, where a 1 corresponds to where we've placed a pattern. So we've taken this 3D structure and we've made it a 1D array, placed ones and zeros, where there's a pattern, where there's not a pattern. We use a sigmoid activation function for the output layer, so you can have probabilities. So you have your outputs, your predicted outputs are going to be some probability between 0 and 1. It won't necessarily be a binary number. So some model results for this. I've just pick some random values of 2, 3, 4, 5 perturbations. And the darker colors correspond to 100%, white is 0%. So you can see there's a little bit, the actual predictions on the left predicted on the right. You can see there's a little ambiguity here. Here, there's a very slight probability that there's this one guy off here. There's a little ambiguity here, then ambiguity in this cluster here. But overall, I would say this is pretty good. Kind of the biggest thing, our next work is we want to improve both of our model results. And going back to this idea that we also want to have this ability to detect anomaly values in our classification problem. And then finally, we have sort of developed this user workflow that we're hoping to wrap this whole package in, which would allow people to put in actual field measurements and get out reasonable predictions. And for that, we have some other algorithms that we've developed that discretize a given topography. And so the idea is that we can put our neural networks to the test in that way. So that is my presentation, and thank you for your time.